In this video, we will start with chapter 6, which is on comparative statics and the concept of the derivative. Section 1 explains to us the nature of comparative statics and why it's important for economists. First, it enables a comparison between different equilibrium states. However, it disregards the process of change from moving from one equilibrium to another equilibrium. Comparative statics can be both qualitative or quantitative in nature, and we compare the two different equilibrium states by finding the rate of change using differential calculus. So how do we find this rate of change and the derivative? First, let's suppose we have a function y which is related to a variable x. Some function of x gives us a value for y. We note the difference with a triangle, which is capital delta. That means delta x is a new value of x minus the old value of x. So x1 is a new value, and the x2, x0 or x0 is the old or original value. So if we have a new equilibrium, it means it was the old equilibrium plus a change in x. To find the rate of change, we need to find the difference quotient. The difference quotient tells us the change in y per unit change of x. That means a change in y given a change in x is equal to our function at the new equilibrium, which is the old equilibrium plus a change, minus the original function over the change in x. So if we look at an example, we know that Fahrenheit is a function of Celsius, and it's specifically 9/5c plus 32. So if we need to find the difference quotient, we need to find So to find the difference quotient, we need to find the function at our original point. We get this by saying CO or C naught, and we simply replace C with C naught. And we need to find some different new point, which would be C naught plus some change in C. Again, we replace C with C naught plus delta C. So our difference quotient delta F over delta C would be equal to 9/5 times CO plus delta C plus 32 minus 9/5 CO minus 288/5. So this is simply this function minus. So that should be minus 32. All of this divided by delta C. So we have 9/5 C naught plus 9 over 5 delta C plus 32 minus 9 over 5 CO minus 32 over delta C. So if we simplify, plus 9 over 5 CO minus 9 over 5 CO plus 32 minus 32. So we are left with 9 over 5 delta C over delta C, and that simplifies to 9 over 5. So how do we get the derivative? The derivative is the limit as delta x goes to 0 of the difference quotient. We indicate this by the limit as delta x tends to 0. This simply means a very small change in x. So if we look at an example, say we have the function y is a function of x, and it's specifically 6x squared plus 4x plus 12. So our first step would be to get our difference quotient. So fx at 0 is equal to 6x 0 squared plus 4x 0 plus 12. And we need to find our new equilibrium. So before we place this into our difference quotient, let's just simplify this. So this will be 6x0 squared plus 2x0 delta x plus delta x squared plus 4x0 plus delta x plus 4 delta x, plus 12. That is equal to 6x naught squared plus 12x naught delta x plus 6 delta x squared plus 4x naught plus 4 delta x plus 12. That means our different quotients is 6x naught squared plus 12x naught delta x plus 6 delta x squared plus 4x naught plus 4 delta x plus 12 minus this function. So it will be minus 6x naught squared minus 4x0 minus 12 divided by delta x. So again, if we simplify, plus 6x naught squared minus 6x naught squared plus 4x naught minus 4x naught plus 12 minus 12. So our difference quotient in this case is equal to 12x naught delta x plus 6 delta x squared plus 4 delta x over delta x. In each of the terms above we have a delta x, so we can divide the denominator into each of the numerator. So we are left with 12x naught plus 6 delta x plus 4. To move to the derivative, we need the limit as delta x tends to 0 of delta y over delta x. This simply means we need the limit of this function for our difference quotient. And to get the limit as delta x tends to 0, we replace delta x with a 0, and we are left with 12x0 plus 4. Section 6.3 is the concept of the derivative and slope. The slope of a function f at point x0 f x0 is its tangent line to the graph of the function at point x0. In economics, this is often the marginal function of productivity, or the marginal cost function, for example.